Hey guys, welcome to Safi Mixed. In this video, I want to solve an exercise as an implication of Newton's second law and will let you know how to model problems and how to apply Newton's second law. And that is in fact a modified form of Atwood's machine, where Atwood's machine is usually an integral part of all the introductory courses in mechanics, which is used as an implication of the translation and rotational motion of Newton's second law. But here we consider a modified form, and I consider a support like this, and then I take a pulley and I hang the pulley from the support with a rigid rod, and then I roll thread around it through several times like this, and then hang it down and attach a body of mass in. And then obviously there are now two different cases, whether we consider the mass of the pulley, that is, we consider the pulley to be either of a negligible mass or the mass of the pulley is considerable. So that is one case. In the second, whether the string is extensible or inextensible, and I consider that the string is inextensible, and then obviously the tension is in the upward direction and the gravity is dragging or attracting the mass in the downward direction with the force given by the product of mass times acceleration due to gravity. And we want to find the dynamics of this particle. So I suppose that the radius of the pulley is r, and the moment of inertia of the pulley is I. That is, I consider the moment of inertia of the pulley, and would then make two other simplification. Now, I can take a reference level, either the ground as a reference level, and locate the position of the mass with respect to the ground to be x at any time t, or I can take this as my reference level and consider the position to be with respect to the support, whichever way it may be. That doesn't make any difference. You can put the position, you can take the position of the particle with reference to the ground or with reference to the support. That doesn't change any equation. Okay, with that said, then I consider that downward direction is positive. And with that in mind, I can find the net force acting on the body as F net equals Ng minus T. And with reference to Newton's second law, this net force must be equal to mass times acceleration produced in the mass. And now the torque produced is given by I times alpha, where alpha is the angular acceleration and I is the moment of inertia of the pulley. And if there is no slipping of the rope or the pulley, then the alpha is in fact given by A divided by R. And if I use this value, then I can write the torque in terms of linear acceleration is I times A divided by R. And since the tension in the rope is perpendicular to R, therefore I can use the definition of torque, which is R cross F equals RF sine theta, and this theta is 90 degrees, therefore sine 90 degrees is 1, and I'm left with RF. So if I put this value for torque, this equation reduced to R, sorry, not F, this is in fact T. So I write this as tension T and write this as tension T. So RT is in fact equal to what equal to IA divided by R. And from this I can find T equals IA divided by R squared, taking R to this side. So now we have a relation for tension in terms of the moment of inertia, acceleration, and R. Now these two quantities are supposed to be known to us because these are the characteristic of the pulley. I and R are characteristic of the pulley. So if we know about them, we can find tension provided we know acceleration, or in other words, we can use the value of T in this one equation to find the acceleration. So I substitute for T at this position and write that equation is mg minus I a divided by r squared equals m times acceleration a. And from this I can write, by taking this to this side, I can write mg equals I divided by r squared plus m into a. That is, first I take this term to this side of the equation, making it positive, and then taking a common to write this into this form. And I can take the LCM of these two terms inside the brackets. So I write that we're here, let me write this here. I can write mg equals I plus mr squared divided by r squared times a. Or I can write mg r squared equals I plus mr squared times a. And I can take one more thing. I can take mr squared common from these two terms to write this is mr squared into 1 for this plus I divided by mr squared times a. Now I can cancel this mr squared with this r squared and this m, and then I first write a, and then taking this to this side would go to denominator, so I write this as g divided by 1 plus I divided by mr squared. So this equation defines the acceleration of the mass pulley system. Now we see here, if the moment of inertia is 0, that is, if the mass of the pulley is negligible, then this term is 0 and acceleration is just equal to g, that is, then this behaves like a free fall. So it is in fact the moment of inertia that modifies the acceleration. So increasing the moment of inertia would reduce the acceleration by that ratio. So in fact, this is in fact the moment of inertia of the pulley through which we can control the acceleration of the mass. Now we can solve this equation further to find the velocity of the mass, and that I can do by writing at in the form of dv of t over dt equals g divided by I plus 1 plus I divided by mr squared, and taking t to this side or subtracting the variables, I can further write this equation in the form dv equal, I can write this as dv of t equals multiplied with dt, and I can integrate this equation between an initial velocity and final velocity. So I should know about the initial condition, and I choose the initial condition such that at t equals 0, v is 0. That is, the system is just released from the static position, from the static states. So I can integrate this, then dv of t from v naught to v of t equals, since all these things inside this factor, multiplicative factor with t, are constant, so I take them out of the integral to write this as 1 plus I divided by mr squared integral from 0 to t dt. This just gives me v of t minus v naught equals g divided by 1 plus I divided by mr squared times t. Or from this I can write further v of t equals v naught plus g divided by 1 plus I divided by mr squared times t. Again, you see, if the moment of inertia of the pulley is 0, then we are just left with vt equal to v naught plus gt, which is the equation of free fall, the equation for velocity of free fall. Similarly, we can write this side as dx t over dt, and then write the equation v naught plus g divided by 1 plus I divided by mr squared into t. And taking t to that side of the equation, I can write this as dx of t and multiply this with dt. And then again, integration between the initial and final positions, I can write this as integral d of xt from x naught to x of t equals, since v naught is the initial condition and velocity, therefore I take that out of the integral and write this as dt from 0 to t. And then again, this is a constant term, so I write this as I divided by mr squared integral dt from 0 to t. And this side would give me, if I integrate this, it will give me x of t, and then substitute the limit would give me x of t minus x naught equals, this would just give me v naught t, and this here is a t, yes, this is t, and this would give me t squared divided by 2. So I write this as g into 1 plus I divided by mr squared into t squared divided by 2. Again, you see, if I, the moment of inertia is 0, this is the straight away the free fall equation for position of the particle. So it is the moment of inertia of the pulley through which we can control velocity, through which we can control the position, change in position, and the acceleration. So this way we use Newton's second law to solve our problem, to model our problem, and that is, in fact, the moment of inertia is the important quantity in this problem. Thanks for watching.